So Hyungjun, you can,
Yes,
we see your screen and we can hear you.
yes.
Sorry, just one thing. Can I ask everybody to turn off the microphone? That way we don't hear any background noise. Thank you, everybody. Okay.
Hyungjun, you can get started. We don't hear you.
Can you hear me?
Right now, yes, but
Yeah.
I couldn't hear.
Yeah. Thanks, Professor Roxana. Hello again. In this hands-on, I'm going to briefly introduce the input flags you will use during this tutorial, and then briefly explain exercise and one problem you will practice. Let me start by showing showing the input page in current EPW documentation site. This page will be updated soon, and as you can see, there are several input keywords in EPW. However, I think essential input are just a few, and here I show one basic input template, including essential input. This template consists of the four blocks, and roughly speaking, the first block is related to the input and output, and the second one is the control of runs, and the third one is related to the linearization, and the last one, the fourth one, is related to the K and Q course grid. The first line is just a comment line, and the second line indicate the EPW input begin. And I think the third line is important, and this third line together with this line of out directory, it constitutes the name of input directory when EPW will load wave functions data obtained in the previous NS steps. It is also a prefix of most EPW output, and also most, but actually not all EPW output. And also the next one, the output input. This output input specifies the directory where EPW outputs are stored, but not all. But most EPW output are stored in this out directory. The next one is the AMS, but you can ignore this AMS input keyword since it is the totally overwritten by the previous data from NSSF calculation. And this means that you can safely ignore this input. And the next one is the DVHSF directory, and as this name means, this DVHSF directory point to the directory where output from Phonon calculations are stored, and all of the necessary output from Phonon calculations can be simply collected by the simple script pp.py. The next one, next input keyword is ELPH. This ELPH input keyword enable electron-Phonon vertex calculation, and importantly, this ELPH is the in default false but in most cases, you need to perform electron-phonon vertex calculation. And this means you have to explicitly include this ELPH is true. But for example, in other case, for example, in calculation of superconductivity, you might need to set this ELPH false. The next input keyword is EPW write and EPW read. I think both of them are very important, and both of them are related to the restart. Are related to the restart. For example, for future restart from the one-year base representation, you need to set EPW write true in your all calculations, and also you need to set EPW read false in this case. Then, after your calculations finished, you have the all necessary file for your restart, and using these files, you can easily restart from the one-year basis when you set this EPW read true and set EPW write false. And as you can see in this diagram, with this input keyword, you can restart from this one-year basis. The next input keywords is totally related to the one-yearization, and I think that maybe all of you know where all these input, but I just want to mention this band script flag. Basically, this is the exactly same as the one-year night input exclude bands. But as you know, where in some case, you need to study some systems with low-lying semi-core states, and in most cases, the contributions from these low-lying semi-core states is not important in your interesting physical quantities, and you always need to exclude these low-lying states by the specifying using this input flag and specifying the list of excluded bands. For example, in your first example, you need to exclude the lowest 5 bands in metallic red. And the next one is the one-year plot. And very unlikely in the PW2 one-year 90 plus 1-year 90, you can easily generate and also directly generate the cube files, including the real space, including the real space 1-year orbitals directly in EPW. And also, if additional 1-year 90 inputs are needed, you can include them by using this keyword of W data, and this is the one example of use of the W data input keyword. Next, Sorry, there was alarm. Yes. Yes. Next one is related to the course on K and Q grid, course on K and Q grid, and in this case, you have no choice. For example, this NK1 to 3 should be exactly same as the number of grid used in your previous NSCF calculations. And also, this input keyword of NK1 to 3 is also should be exactly same as the number of used, the number of grid used in your previous Phonon calculations. But there is one thing that you have to meet. For example, this course K grid should be commensurate with this Q course grid. And also, the number of K grid should be greater than or equal to the number of Q grid. Yes. For example, in this case, you cannot use the number of course Q grid 4, since the 4 is not commensurate with 6. And then with respect to the previous basic input template, for example, if we want to plot electronic bands and phonon dispersion, in this case, you just need to add band plot input flag to this basic template. For example, you need to set band plot true, and also you need to specify the K or Q point list, and these data should be included some additional files, and the name of these additional files should be specified by these PKF and PQF input keyword. And for example, if we want to plot electron-phonon vertex along some K or Q point path, in this case, you just add this PITGKK flag to the previous basic template. For example, you need to set PITGKK is true, and also you need to specify the K or Q point to the data. And the next example, for example, if we want to calculate the Phonon self-energy within the delta approximation, in this case, with respect to the previous basic template, you just need to set Phonon self and to true, and also you need to set delta approx is to true. And also, as you can easily from the expression of the Phonon self-energy, when calculating Phonon self-energy, you need integration over K points, and also you need to sum over the band states, and also you need to include the two delta function. And this means additionally, you needed to add the input flag, D Gauss W, which is for the Gaussian width of the Gaussian function for the approximation of delta function. And also, since you need the integration over k points, you need to specify k, and also since you need to evaluate the self-energy at each Q point, you need to also specify Q point list. And this is done by this part. And also looking at this summation over the band state, you can include you can introduce the Fermi window, such as the input keyword FSC. In this case, if we introduce this FSC input keyword, in this case, you can consider only state within some range around the Fermi level. For example, within Fermi level, within Fermi level plus minus FSC. And lastly, as you can see, in this expression, the temperature is not included in this expression. So you can safely ignore this temps input keyword, which is related to the temperature. Lastly, if we want to calculate electron self-energy, in this case, as you can see from this expression, first, you need to add this input keyword and set it to true. And also, since this expression also includes the delta function, you need to add the Gauss W input keyword. And also, this expression needs the k-point evaluation and q-point integration. You need to add the k and q-point list. And also, this expression included the summation of band states. And also in this case, you can use the input keyword of FSC. And in this case, as you can see, the temperature is included in this expression, and you need to add this input keyword of temps, which is related to the temperature. And lastly, as you can see in the expression, this expression includes the Fermi level, and usually the Fermi energy is calculated internally in EPW, but in other case, you can specify explicitly the Fermi energy, and in this case, you need to set if Fermi read input keyword to true, and also you need to specify this Fermi energy input keyword. And yes, this is the supplementary information. As I already said, first, I want to mention about the restart input flex. In addition to the EPW read and EPW write, there is another input keywords, EPB read and EPB write. And with these input keywords, we can restart from Electron-Phonon vertex in the coarse block basis. But in most cases, this restart is not useful. And as I said, in most cases, you need to restart starting from the 1A basis by using EPW read and EPW write. And also, currently, in EPW, there are several restart flag, and I think that they will be covered during the hands-on session. And the second one is related the specification of K or Q points. In this case, in general, we have three choices. The first one corresponds to the gamma center regular grid. For example, in case of a coarse grid, you can specify regular grid by using NK123 and NQ123. But as I said, NK123 and NQ123, in this case, you have no choice. Both of them should be exactly same as your previous NS-SAFE and Phonon calculations. In case of the fine grid, there are the additional input flags, NKF123 or NQF123. For example, using NKF123, NQF123, you can introduce the gamma center regular grid on dense grid case. The second one is the correspond to the explicit inclusion of K and Q point list using the additional file. For example, this is one example, and both cases have the same format. For example, the first line has two fields. The first field corresponds to the number of K or Q points, and the second field corresponds to the unit. For example, in this case, you have two choices. The first one is the Cartesian 2 pi over A unit, and the other is the crystal unit. And the first column represent the weight or the K or Q point weight, but usually this first column of weight is not meaningful. The third case is correspond to the random grid, but this will not be used in the tutorial, and I think that maybe this random grid will be covered during the hands-on session. And lastly, supplemental information is related to the polar collection. For example, if we set L polar input flag to true, then in this case, this input keyword make the correct one interpolation in case of polar materials is possible. For example, in exercise 2, we consider the silicon carbide, and since silicon carbide is a polar material, you need to include this polar input flag. And this is the summary of the 2 exercises and 1 problem. The motivation for this exercise and problem is to I hope all of you practice for how to check the quality of one interpolation of physical quantities for your future products run. And in exercise 1, we consider metallic lead, and in this exercise, we compute electron and phonon band structures and phonon line widths. And in this case, these band structures will be calculated by using the phonon code and the phonon code and the PW code, and you need to compare between the phonon code result and the EPW calculation. Then in exercise 2, you consider the polar insulator, the silicon carbide. In this case, additionally, you will compute the electron-phonon vertex on selected the symmetry lines when using the EPW and the phonon code. And finally, you need to compare them. And the last one is problem. This is also consider silicon carbide, but in this case, you will compute electron-phonon vertex, but in this problem, you need to use the different wave vector for initial state. For example, in exercise 2, you will use the gamma point for initial states, but in this problem, you will consider the different wave vector for initial states. The motivation for this problem is to make sure that you realize that in most cases that you encounter a very different convergence behavior depending on the computational details. For example, the initial state. Maybe you can start now.